So I hope this is working. Yeah. Okay. Cool. Thanks for the nice introduction, Ricardo. So this talk is about applying cloud-native operational model to the infrastructure layer in the telco environments. And telco workloads, as you may know, they have like unique requirements: ultra low latency, deterministic networking, strict SLAs, and also extreme scale when it comes to, because there are distributed sites. So the challenge is not just about running the workloads or applications, it's also about provisioning, managing, and upgrading the infrastructure and clusters with the same declarative pattern. And today, my plan is to walk you through how we achieve that using open source toolings, mainly Kubernetes, Cluster API, and Metal3, the project that Ricardo mentioned. So a few words about myself. I work as an open source architect at Ericsson Software Technology. I'm also one of the maintainers of the project called Metal3 or metal3.io. And I'm also co-chairing the CNCF Technical Advisory Group for Infrastructure. What I'm presenting today comes from the operational experience that we are gathering in Ericsson as we have the real deployments. Also, that means real failures, and then also real scale. And being maintainers, we also see how open source is evolving and evolving in different industries, and especially in telco, and how it's also driving some of the most demanding use cases when it comes to features of some of these projects. So I think many of you are already familiar with this telco journey that we have seen, or the journey of the infrastructure and how it has evolved in these distinct different phases. So as you can see, in the early days, network functions were very tightly coupled to the proprietary hardware, and they were deployed as vertical appliances, so they were mostly completely siloed. But then we also saw virtualized or network function virtualization, as we call it, which brought a bit more flexibility for the workloads, but they were still bound, or they are still bound to VM-centric operational models. And then at some point, we also had some disintegrated or disaggregated, I would say, phase where we had the control plane and the user planes were running in separate entities, but then still they were running on top of VMs, to currently what we see as the cloud native or the containerized network function, which brings about the real transformation, microservices, and of course the infrastructure has also become declarative, which I will show in the next few slides, automated and distributed. Most importantly, this change also changes the failure model, for example. So we rely on orchestration and reconciliation instead of, let's say, manual lifecycle management. And this is the shift what enables to scale operations massively. So I'm going to talk about a bit of the telco challenge that we are, or that we have over a long period of time. Unlike a single data center, telco infrastructure is actually, as you can see, it's spanning from central clouds to more aggregation sites and even far edge locations. And each of these tiers have their own latency and regulatory constraints. You have real-time traffic data, which requires deterministic packet processing and predictable performance. And we must assume that hardwares might, or almost always it will fail. There would be network partitions, for example. There would be stretched cluster, as we call it. And of course, there is also vendor variation. So managing thousands of these servers, mostly bare metal, manually it doesn't scale. The lifecycle management or lifecycle automation, it becomes mandatory. So designing around failure domains across racks, sites, regions is also as important as provisioning for the capacity. So the challenges that we mainly face here is, first, of course, the scale. Provisioning a few servers is trivial, as we know. But when it comes to provisioning hundreds and thousands of bare metal servers across different sites, automatically, it is a big challenge. Then comes the life cycle management of this, because we know, as I said, hardware would fail, NICs might die, firmware might become outdated. So all of these must be handled programmatically. Then there is, of course, this downtime and the famous 5 nines, as we all know, for the telco that comes, that there must be almost or none, like there would be zero time downtime. And then you can't just take down a telco core during, let's say, an upgrade. So you need to have the HA strategies, and it must be built both at the application layer, but as much as also in the infrastructure layer. Then fourth is the security and compliance, of course, because as we know, telco is a very highly regulated industry. Everything from the data to sovereignty to lawful intercepts, everything has to be respected in this sense. And then, of course, there is this multi-vendor environments where because telcos across the globe is buying hardware from different vendors. So that means you need to have some sort of open interoperable automation rather than, let's say, a single vendor stack. And these challenges drives towards more cloud native and open source approach. And hence, this layered model captures why telcos need a hybrid architecture. Network functions at the top that I'm actually showing here, it implements the actual logic of the telco applications like UPF, IMS, packet core, for example. And these depend on the platform for the resilience and the performance. But then Kubernetes supports the containerized network function workload with elasticity and orchestration. And then you might still ask that why I do have a virtualized layer still there, but because not every application has still adopted the, like, let's say, the cloud native world yet. There are still some applications which still tend to run on the VMs, and hence we have also this sort of approach where virtualization still continues to run VNFs while we are trying to transition or migrate from that to the CNF world, which then the focus next would be on the bottom layer here, the specialized infrastructure. And when I am saying, or why you may ask that we are going towards bare metal management, because as I have shown you in the previous slide as well, the telco applications need features or toolings for, let's say, NIC acceleration or CPU pinning, for example, or DPDK or SRIOV to meet these performance guarantees. And hence, the important part are not just running the workloads, but also the lifecycle management of the workloads as well as the infrastructure across the entire stack, from platform to virtualization layer to physical hardware. And hence, we use the Kubernetes native interfaces to unify these layers and automate the provisioning of the servers. The philosophy here is that we need to treat the infrastructure like applications. So infrastructure is declared in YAML. I will show you how we are doing that in the Metal3 project, reconciled by controllers, and also, of course, having the using the Kubernetes to maintain the lifecycle of the infrastructure as well. In this slide, I don't want to really advertise anything about the Ericsson product, but then the main thing that I wanted to highlight is the lifecycle management part, and this just captures some of the open source tools that we are using for the product in-house. But it just shows that we have chosen Kubernetes as the standard platform for running containerized network functions. And the reason here is not just scheduling and orchestration, but also providing declarative API services as the reconciliation model. And as I've already mentioned, a couple of these projects, Cluster API, we are using Metal3, and of course, we are also using the Cluster API provider OpenStack. The choice is, again, to make sure that we invest in managing the Kubernetes way of these infrastructures and platforms for the applications that we deploy on top of that. So again, bringing back the previous architecture, it more simplifies the projects that we are now putting in these unified infrastructure management. The projects, of course, as I mentioned, is cluster API, which orchestrates the life cycle of the clusters and the control planes and the machines. And then, of course, we have Metal Cubed on one hand for the bare metal management, but we are also using cluster API provider OpenStack. I'm not going to talk too much about that in this talk. I will mostly focus on the Metal Cube or the bare metal part. But the intent here is that the provisioning on a telco side is because the key takeaway for this would be that the architecture is same for managing a Kubernetes cluster and the bare metal or the physical hosts. The same reconciliation pattern that is we are using, which is running the application, also to use the reconcile the infrastructure itself. So before jumping in, though, I just wanted to have an idea of how many of you have previously heard about Metal Cubed project. Okay, of course, Ricardo, you have. Yeah, so I think fair enough. But then I will just again briefly talk about how it, what it does and where it fits in the CNCF ecosystem. So this diagram shows the full bare metal provisioning stack. Metal Cube actually integrates at the bottom when you have the server. It integrates with the very powerful tool called OpenStack Ironic, which is the main engine which provisions the physical hosts. And then there is, we have a controller which exposes these Ironic APIs inside Kubernetes. This is called bare metal operator. And bare metal operator is reconciling an object which is called bare metal host. And bare metal host is actually a YAML representation of this server inside Kubernetes. I will show an example also in the next slide. And then we have a plugin for cluster API. There is a cluster API provider for Metal Cube. And then we also have an IP address manager for the static IP address management. And then, of course, at the top, we have a cluster API. So a brief word, I think most of you are already familiar of cluster API and the power of the provider model that it has. But then again, I will just briefly introduce. Cluster API is abstracting the cluster lifecycle as we know it as Kubernetes objects. We define the management clusters, and then you would have a target cluster which will then become a workload cluster itself, or it can manage other clusters also. And then the best thing about this is that once you have a target cluster, then you can also do the move or pivot and make it so that it is self-manageable. In a sense, you don't need any management cluster. But if you still do have a use case to manage your manage the life cycle of the target cluster centrally, you can still keep the management cluster for, let's say, edge-based deployments. And as I have said, that the most powerful thing about cluster API is the provider model. That you can deploy a cluster API-based cluster as you would do on any of these public clouds like AWS, GCP, and Azure. All of those public clouds have a provider for that. But prior to Metal Cubed, there was no API to represent, let's say, a bare metal server or provision a bare metal server using cluster API. So we were one of the first, if I'm not mistaken, bare metal providers in the cluster API space. And as I have already discussed that, we had an API which represents the server, which is bare metal host, and then we became the API using those declarative models, and then we also have a reconciler called bare metal operator, which I'm going to talk about soon. And then when it comes to Metal Cube, as Ricardo also mentioned, that it has become a CNCF incubating project very recently. It is providing the interface for provisioning your bare metal hosts through Kubernetes. It is a CNCF-focused project focused on bare metal provisioning and lifecycle automation. You have self-hosted, self-managed, infrastructure-aware reconciliation in the cloud-native space using Metal Cubed. And of course, it has a cluster infrastructure provider for cluster API. And the the critical concept that we try to advertise here is that the bare metal hosts are, or the bare metal servers are also the first-class Kubernetes objects. And we are still in the Kubernetes ecosystem when we are managing these physical machines or provisioning these physical machines. So the clear concept, I think, or the very easy concept would be that you have a bunch of bare metal servers, and then you want to deploy a Kubernetes cluster on top of that. And how you do that is by you represent your bare metal host or bare metal server in Kubernetes using this YAML. There are a few pieces of information or requirement that you must need to give. For example, the baseboard management controller address and credentials, so BMC. Address and credentials, and also I think the boot MAC address, which is the requirement. And once you have given that, there is a reconciler in MetalCube called bare metal operator. It will start reconciling the states as you have wished in your YAML representation regarding what image you want to provision, how many of the nodes you want to provision as control planes, and all the so on and so forth. It's the same way you would be deploying a cluster using cluster API in even, let's say, any other public cloud, or same as you will manage a VMs in any other public cloud. And the cluster API provider workflow, as I have mentioned, then in cluster API, a representation of a Kubernetes node is called machine. And in this case, for the cluster API provider MetalCube, the idea is that you want to represent a machine and deploy a Kubernetes cluster on top of the bare metal servers. And as I have already shown you, that cluster API can do or manage these provider same way it would be actually deploying a VM. But here we are only concerned about the MetalCube. So we have an operator, which is this bare metal operator, which is reconciling the object inside the Kubernetes called bare metal hosts, and then it is provisioning the Kubernetes cluster on top of that. And few words about the bare metal operator, because I have mentioned it so many times here, that so this is, as I have said, on the left side of the picture, that it is reconciling the objects. You have given the baseboard management controller address and the secrets and all the requirements that is needed for bare metal operator to manage this bare metal server. And then it interfaces with Ironic, OpenStack's Ironic, and you don't need to bring along Ironic when you are deploying MetalCube. It is deployed as part of the MetalCube stack, and it is being managed by MetalCube, so you don't need to worry about interfacing with it. It is done automatically. And then it talks with the BMC, and then you have a very important component here, which is called the deploy RAM disk. We also call it the Ironic Python agent. It is the agent which runs on the bare metal server while we are doing, let's say, the virtual media booting or PXE booting. And then it performs very interesting and essential operations like hardware inspection, for example, and gives you back what sort of hardware or what sort of NICs, for example, or those kind of details that you have on the server. And it also does one important thing is it provisions the image. So while you have given some operating system to be provisioned on top of this bare metal server, it copies that into the local disk and then tries to reboot it on again with that host image. So since this was mostly about the day 0 or day 1 operations that provision a bare metal server and maintain the life cycle of it. But when it comes to day 2 operations like upgrade, recovery, and remediation, and these are very important, again, when it comes to the telco infrastructure as well as any other applications. It's not just about creating clusters, but it's also about talking or managing these challenges. But with Cluster API and MetalCube, we are also handling the control plane and the worker upgrades in a rolling fashion without impacting the workloads. And then it's the same as you would be, imagine that you would be expecting from a VM or a public cloud VM would do. You can drain a failed node. Same way, you can reprovision and make sure a server is rejoining automatically. And we are also have recently added a feature around failure domains. So loss of a rack, for example, doesn't or shouldn't impact the HA strategies. All of these features that you see here is driven through the same approach that we are not mostly thinking about SSHing into the nodes and rebuilding the clusters manually, but it's rather, and not even running playbooks in that sense. It is rather the Kubernetes control planes which are driving these operations on top of the clusters, like upgrades and provisioning and remediation. So we have a remediation controller as well in Metal3, which is doing this sort of remediation. But as you can imagine, in case of bare metal world, the challenges are pretty unique. So it's very easy for a public cloud VM to just like spin up a new VM. But then in bare metal servers, you don't want that. You want to really check what is the issue inside the VM. So you want to do this kind of operations like rebooting and remediation and checking. And even if something is not coming up in a significant amount of time, then we also have a way to make sure that you cut out the node from the cluster and then manage it separately and then bring it back inside the cluster. I have a very simple demo, or just to show what Metal3 is doing. It's not as fancy as we saw Casper's demo from the previous talk, but I had just pre-recorded it. So in the screen, what you are seeing is that how we are managing this in our CI, for example. So of course, because we are doing this in the Metal3 CI in a say that it's not really a bare metal server, but we have virtual machines which we treat as the bare metal servers. So we are not talking to the virtual machines using the wish commands, but we are using let's say tools like virtual BMC for PXE booting, VBMC, or we are using Sushi tools for virtual media booting, these VMs. So we are treating these VMs as it is a bare metal server here. So you can see that there are two nodes in the bottom right corner, node 0 and node 1. These are the VMs. And then inside the Kubernetes cluster on the top right view, you have the bare metal hosts that are deployed, which is representing these VMs, which we call the bare metal servers inside the Kubernetes cluster. So node 0 and node 1. The current state of those two bare metal hosts is available, and they are both online true, means that they are already in a running state. And on the top right view, you have a very simple script where you have a function called start VM, which is doing nothing but patching the online state of this object, which you see on the top right. The online spec is patched. If you are starting the VM, it is patched to true, and if you are stopping the VM, the online spec is patched to false. So the idea of this is to show that when we are calling these kubectl commands, and then how bare metal operator is reconciling and doing the operations on these bare metal hosts without touching any wish commands, but purely using the Kubernetes or kubectl commands. So the stop will patch, and you will see a change in the online spec to false, and then that will make sure through this BV, as I said, VBMC and Sushi tool, that the VMs here are also shut off. And then you will see the same when we are actually patching the online to true. So bare metal operator is reconciling those objects, and the VMs are coming back. And then this is also on the top, on the right bottom corner, you will see the PXE booting has started, and then it is also spitting out the serial logs in the VM. So this is this deploy RAM disk or ironic Python agent running on the node, and then it is doing the, as I said, inspection and those kind of operations on the VMs. And the same way, we also do the provisioning and deprovisioning of these nodes. So I will just jump through, and then this is one of the I have just like skipped through the main details, but the idea is to show that we can also do the provisioning of the operating system image here on top of these nodes using these using the APIs and kubectl commands only. Yeah, so the provisioning has started, and I think soon you will see that Ironic Python agent here is running and copying the copying the operating system image on the disk on the nodes, and then it will start to reboot once the copying is done. And here you see that it's powering it down and trying to reboot it, and once it reboots with the operating system image, the nodes gets in the provision state. Yep, so this is now booting, the node is booting using the operating system that I wanted it to boot you, and then once it boots it, it also runs the cloud in its scripts, and then with that we also get the Kubernetes cluster. So I just wanted to give a brief overview what has recently happened on the Metal3 side. So we have worked on the V1 Beta 2 support for the cluster API. There has been work ongoing for multi-tenancy. There has been also work ongoing on switch management and improvements to this IP address manager and pushing this as one of the IP address manager for cluster API. We are working also towards DHCP-less provisioning, NIC firmware updates, deployment simplification. So one of the things that we also have worked recently is the deployment simplification of Ironic using Ironic standalone operator. The goal of all these improvements is to reduce the operational effort even further and support more complex deployment environments. So again, I wanted to bring back this return to the cloud-native telco message. The biggest value is full end-to-end automation. Provisioning a site involves, the idea is that it should not involve a manual configuration. And using Metal3 and CAPI, we have been able to at least enable consistent tooling across bare metal virtualization and cloud. So the same operation patterns are to be seen everywhere. And declarative infrastructure is what is unlocking this whole distributed deployments. The key takeaways is that provisioning at scale, it requires designing around failure domains. Zero downtime upgrades and of course the remediations are mandatory for telco environments. We of course have these use cases or edge use cases where you need to deploy the single servers, and for those the zero downtime achieving is really problematic, but we are still working towards that. And then of course breaking apart these monolithic systems into microservices and cloud native building blocks improves the reliability and lifecycle control. The momentum forward or towards open source implementation is accelerating because it eliminates, as I already told, the vendor lock-in as well as it also increases the agility. Before I wrap up, I also wanted to just mention briefly about this use of, I have known from Ricardo and others from his team that CERN is using OpenStack Ironic heavily also. And one of the investigation that we did was to test the scalability of Ironic. And as I have already told you that the reason Metal3 exists is that we are exposing the APIs of Ironic in the Kubernetes world. And then this study was heavily influenced by how CERN was using Ironic, because CERN used Ironic with thousands of servers even before we started thinking about it. And these scalability tests that we have done inside Metal3 was also heavily influenced by the learnings that we did discuss with some of the CERN folks. And then as a result, we also have been able to incorporate those in our CI and in our Metal3 as a feature. You will soon be actually seeing those being used instead of deploying Ironic vertically, we take out some components from Ironic and deploy it in a different way so that it can also scale these 1,000 number of nodes, for example, in the clusters. So thanks to CERN for that as well. Well, with that, I think I am done with all. Thanks a lot for listening. Thank you, and I can welcome any questions.
Thank you, Kashif. Yeah. So yeah, really interesting things. I think it's a really nice talk to also describe how far we came with the supporting bare metal and cluster API and all of this. Any questions? We have time for a question or two. Yep, there is one there.
Hey, okay. So I do have one question. Currently, do you use the host firmware CRDs to do the firmware patching as well, or is that something that is only running on alpha and you don't currently experiment within Ericsson?
So host firm, I didn't get the part. So we are using host firmware CRDs for what?
To do the firmware patching on the bare metal nodes. Or is that something that you manage, I don't know, with OpenManage or with Redfish scripts? Currently, MetalCube is exposing the host firmware components.
Yeah. I kind of understand. It should be possible, but I was just thinking if I have a direct answer to that. Possibly I have to check back. Yeah. I don't think I have the right answer for you right now.
And I do have a follow-up question. I noticed that you recently merged the failure domains. However, we had this issue in the past that, let's say that cluster API doesn't recognize when a failure domain is not available, and it will still try to deploy their KCP control plane. Is that something that you manage on the MetalCube side by deprovisioning, like removing the status automatically?
So as I have said, so the failure domain, currently what we have implemented, if I'm not mistaken, is supporting the cluster API failure domain feature in that sense. But then when it comes to remediation, like as I said, there are ways how cluster API remediates the nodes, but then we also have our own remediation controller, which also takes the use cases beyond what cluster API would actually do. But for the failure domain use case that you mentioned, I think we need to have a discussion and see if we are missing something from the bare metal perspective which you would like to see, and probably we can write up some features about that as well. So thanks for bringing that up.
Happy to.
All right, that sounds like a perfect follow-up topic for our interactions in the breaks. I would like to thank again Kashif for speaking at our event. You get our Escalade Marmite and also a tape. Hope you have the Higgs boson there. If not, we'll find a new one for you. Thank you very much. We can thank Kashif again. Thank you.
Thank you.